Right. Welcome back to Honors Calculus. In this video, we're looking at continuity. Finally, we are getting to that point that we said limits were all about. We have all the tools that we need to talk about what it means for a function to be continuous, at least in most cases. There is one aspect of continuity and one aspect of limits that will come a little bit later, but I wanted to kind of put a bow on what we have so far. So without further ado, let me get my head out of the way and let's jump right into the definition. Let f be any function, any real valued function of a real variable. We'll say that f is continuous at a point c, some point in the real numbers, if and only if each of the following are true. And there are three properties. The first property requires that f of c is defined. The second property requires that the limit as x approaches c of f of x exists. Right? Those make a lot of sense. Right? If the function is not defined at a point, then it's certainly not going to be continuous, right? If you're trying to draw the graph and you're thinking back to that definition of a continuous function is one you can draw the graph of without lifting your pencil, well, if it's not defined somewhere, you have to stop drawing the graph. Limit exists makes a lot of sense. The whole point of limits, as we talked about in several videos, was building up the tools for talking about continuous functions. So if the limit doesn't exist, then the function is definitely not going to be continuous. And then thinking back to that one problem when we were talking about piecewise defined functions. It's possible to have a function where the limit exists but disagrees with the function. And that doesn't make sense for a continuous function, so we need to make sure that we exclude that as well. The limit as x approaches c of f of x is equal to f of c. When it comes to trying to use this definition, it turns out that that third point is really all we need. If we can show that the limit has a value that is the value of the function, then along the way, we must have shown that the function has a value, and we must have shown that the limit exists. Otherwise, there'd be nothing to be equal. So even though there are three properties, it is generally the third one that we show, and if we can show that, then the other two are implicitly also true. Showing that one of those first two properties is not true is a nice way of showing that the function is not continuous without having to do anything else. Right? But there we have it, a formal definition based on the axiomatic theory of real numbers of what it means for a function to be continuous that no longer has to rely on the hand waving. You can draw the graph without lifting your pencil because we usually don't even care about drawing a graph. All right, so let me get my head out of the way and let's take a look at a couple of examples. Oh, I'm sorry, I'm getting ahead of myself. Before we get a couple of examples, a few more definitions related to this. We say that x equals c is a discontinuity. Of f of x if and only if x is not continuous at C. A discontinuity is called removable if and only if the limit actually exists. All right. So if all three of those properties are satisfied, then we have a function that is continuous at that point. If at least one of those properties is not satisfied, then we have what's called a discontinuity. If at least the second property is satisfied, even if the first or the third property are not satisfied, we label that discontinuity as removable. And that's what we saw in that example in a previous video. I don't remember specifically what function it was. It was something like f of x equals x if x is less than 1, 0, if x is equal to 1, and x squared if x is greater than 1. And we saw that the limit as x approaches 1 of this function is equal to 1, but f of 1 is equal to 0. Because the limit and the value of the function do not agree, the function is not continuous. But because the limit as x approaches 1 of f of x exists, x equals 1 is a removable discontinuity. All right. So that's what we're talking about with a removable discontinuity. A removable discontinuity is the type of thing that if you try to graph it using software, you can't see the problem right away. For a lot of the things that we're going to be doing throughout the rest of this course, a graph that has, or a function that has a removable discontinuity, it's going to turn out that we can treat it as though we have removed that discontinuity. We can just ignore that point, pretend that it works the way the limit does, and as long as there are finitely many places where that happens, then we don't have anything to worry about, and we can treat the function almost as though it was continuous for a lot of the tools that we're going to be analyzing, or at least some of the tools we're going to be analyzing. But for today, let's move onward and look at a few more definitions, because continuous at a point or discontinuity at a point is important. But when it comes to continuous, one point is not really all that useful. Instead, we're going to be looking at continuous on an interval. We can say that f is continuous on an open interval AB if and only if f is continuous at every point C inside that interval. Closed intervals are a little bit messier. We say that f is continuous on the closed interval from A to B if and only if, and this time we're going to need two conditions, I guess three conditions. The first condition is that f is continuous on the open interval from A to B, and the limit as x approaches A from the right of f of x is equal to f of a, which necessitates that the limit exists and f of a exists, or at least the one-sided limit exists. And three, the limit as x approaches b from the left of f of x is equal to f of b. Again, which necessitates that the one-sided limit exists and the function is defined at that endpoint. Right, we use one-sided limits for those two endpoints because on the other side of the interval, who knows what's happening. A classic example of continuous on a closed interval is something like a square root function. Right. The limit as x approaches 0 from the left of the square root of x does not exist because the square root of x is undefined on the interval negative delta less than x minus 0 less than 0. Right? The function is not defined anywhere there, so we can't satisfy that definition of the one-sided limit. So the one-sided limit of square root does not exist from the left, but the limit as x approaches 0 from the right of the square root of x is equal to 0, which is exactly what you get if you evaluate the square root of 0. So the one-sided limit exists so we can have continuity at that endpoint of 0, even though the function is not defined if you go anywhere past it. And one last piece of vocabulary is continuous everywhere. A function is continuous everywhere if and only if it is continuous on the interval from negative infinity to positive infinity, which we've established before is the set of all real numbers. But using this, we can rely on the definition we've already come up with for continuous on an interval, and everything works out nicely. All right. So problems on continuity are generally going to ask things like, is the function f of x, and let's define this as a piecewise function, f of x is equal to 0 if x is less than 0, x if 0 is less than or equal to x is less than or equal to 4, and f of x is going to be equal to negative 1/4 x squared if x is greater than 4. All right, so we have this function. It's a piecewise defined function broken into 3 pieces. And we're asking, is this function continuous everywhere? For the sake of time and expediency, I'm not going to go through and prove to you that every polynomial is continuous everywhere. But I think that you can see, based on what we've talked about with limits, the limit of a polynomial is just evaluate the polynomial at the limit point, which is exactly what it means to evaluate the function at the point. So yes, polynomials will be continuous everywhere. And that's going to be our starting point, our basis for everything else we're doing here. A polynomial is continuous everywhere. And 0, x, and negative 1/4 x squared are all polynomials. So the only places where this function may not be continuous are the breakpoints. X equals 0 and x equals 4, right? The two places where the piecewise defined function jumps from one piece to another. And we can evaluate each of those pieces. The limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the left of 0, which is 0. The limit as x approaches 0 from the right of f of x is equal to the limit as x approaches 0 from the right of x, which is 0. And finally, f of 0 is equal to 0. 0, 0, 0, everywhere 0. So we are continuous at x equals 0. Try that again with x equals 4. The limit as x approaches 4 from the left of f of x is the limit as x approaches 4 from the left of x, which is 4, and the limit as x approaches 4 from the right of f of x is the limit as x approaches 4 from the right of negative 1/4 x squared, which is negative 4. All right. The limit in this case does not exist. And because the limit does not exist, we have an essential discontinuity, not a removable discontinuity at x equals 4. And so the function is not continuous everywhere because it is discontinuous in at least one place. All right. Before I wrap up this discussion of continuity, I want to take one more look at g of x, 1 over x. We've talked about this function before. Of course, g of 0 is undefined. 1 over 0 is not a defined operation. So x equals 0 is a discontinuity. But I wanted to bring this up anyway. It's not going to help us in our search for continuity because the limit as x approaches 0 of g of x is irrelevant. We already know that the function is discontinuous. But that doesn't change the fact that I don't know how to evaluate that limit. So there's some work to be done here. There's still a couple of things on limits that we still have to talk about, and we'll be talking about those in a couple of future videos. But for right now, I'm going to wrap up this discussion on continuity by giving you a problem to try on your own. And so I would like you to take a look at this function. H of x is, I wrote that backwards, sorry about that. Let me get in there and correct it and make sure you're doing the right thing before I set you loose. I want to look at 1 over x minus 5 if x is less than 0, x minus 1/5 if x is between 0 and 5, and 5 over x minus 1 if x is bigger than 5. And I would like you to find the largest interval which contains x equals 0 so that this function is continuous on that interval. All right, take a few minutes, see what you can come up with on that one, and I'll see you in the next video.